chapter 9. I know this learning style might be difficult for some of you guys not in the classroom discussing and talking about these concepts, but I just want to go over chapter 9 before we take a test on it. Our test will probably be Thursday or Friday. Hopefully you finish your review questions and your worksheets, as we'll be going over those over the next few days to prepare for our test. If you haven't finished them and we go over them, you won't be able to receive credit for it. So please get those in as soon as possible. So let's just jump in. 9.1, conduction. All right. So easy to remember: conduction, convection, and radiation. Conduction meaning direct contact. Convection meaning through air, and radiation is through like the sun, coming from the sun and light. Okay, so talking about conduction, the heat of her hand is warming up the glass, but because it's not in direct contact, it's not gonna she's not actually touching the wine in this glass, so it's not going to make the wine much colder, but she's just touching this long stem of the handle. Okay. Snow is a poor conductor because its flakes are formed of crystals that trap air and provide insulation. All right, so anything that is an insulator is a poor conductor. So if you think about wood is a good insulator, but it's also a poor conductor of heat. Okay, whereas metal is a poor insulator, meaning it doesn't hold heat very well, but it transfers heat very well. All right, so that's why we make our pots and pans out of metal, because they're good conductors. Right? This is also why we use wood when we make a fire in our house, because it is a good insulator. The wood will hold on to its heat, all right, so that the house can stay warm for longer. All right, so it's important to understand different between conductors and insulators, but and that's right here: conductors of heat versus insulators of heat. All right, solids or metals, these are good conductors. All right, others, poor conductors are good insulators. It's always the case. Okay, so the three types of heat transfer: conduction, convection, and radiation. All right, so let's move on to the next section. Convection, right? Convection is, heating. Well, here we go. Transfer of heat by the motion of fluid as it rises or sinks. All right, so if you can look here, you can see the water. You can see the convection going on, right? Conduction is the transfer of heat to the pan, but then the transfer of heat in the fluid, right? That's convection, right? Transfer of heat through the air, that's convection. Okay, so conduction. Whoa. Sorry, don't know what this is. Sorry about that. Okay. Here's the tip of a heating element, and you can see the convection molecules in the water. All right. So convection is through a fluid or a liquid. All right, through air. Okay, like in an oven. We call that a convection oven. Why? Because the heat is, the air is being heated, and it is increasing the temperature. All right. You can see from this, this lady, she has her hand up above, because as the heat leaves here, if she put her hand right here, she would burn her hand very badly. Okay, but because she has it up here, the gas cools off and isn't as hot by the time it gets to here. Why? Because it's expanding, because it is convecting, right? The convection, the air is spreading out. Okay. And then moving on to radiation, right? Radiation is, the transfer of energy. Right here, if the transfer of energy cannot involve conduction or convection. Why? Because there's not enough. You can't heat up all of the particles in the Earth, in the Earth's atmosphere, right? And the energy is traveling from the sun through space. All right. There's nothing in space. There's no particles or no fluid for the sun to heat up. So because there's no fluid, it can't be convection, right? There's no direct contact, so it can't be conduction. So this is our third type of energy transfer we call radiation, right? And the transfer of energy we call radiant energy. All right? This exists in the form of electromagnetic waves. In chemistry, you'll learn about the different types of electromagnetic waves. All right? And there's a whole spectrum of them. All right? And in the middle of the spectrum is what's called the visible spectrum, which is what we actually can see. All right? The colors that we actually see: red, orange, yellow, green, blue, purple. All right? Those are visible waves. There's ultraviolet waves, there's X-rays, gamma rays, microwaves, right? Radio waves, infrared waves, right? So, those are all the different waves. We learn more about those in chemistry. But you can see a long wavelength is cool, a medium wavelength, and then a hot wavelength is short wavelength. So which one would have the highest frequency? This one, shorter wavelength equals higher frequency. Okay? So, if you look at the temperature, all right, so the frequency, the more frequent, the hotter the temperature. Now, understand, all light, all radiation travels at the same speed. So this light is moving from here to here to here. It's all moving at the same speed, okay? But if it's all moving at the same speed, this one has a farther distance to travel than this one does. So the shorter the wavelength, right, the cooler the temperature, right? But they're all moving at the same speed. All right, all light moves at the same speed. All right, very important to understand. Here's some frequencies, right, of the wavelengths, and in this area, this is what we call visible light. This is the visible spectrum. Okay, here's temperatures: 3200 Kelvin, 2400 Kelvin, 1600 Kelvin. Okay, different temperatures of radiation. All right. Moving forward, absorbing energy. Okay. Good emitters of radiant energy are also good absorbers. Poor emitters are also poor absorbers. For example, a radio dish antenna constructed to be a good emitter of radio waves is also a good receiver of them. All right. So something that is poorly designed for receiving will also be poorly for transmitting. Okay. All right. Moving forward. Radiation that enters the opening has little chance of leaving because most of it is absorbed, for the reason of the opening to any cavity appears black to us, right? Because it doesn't leave, okay? Why? Because there's such a small little hole opening here. Now, if you can imagine radiation coming into the earth, this is the reason why people say that smog is bad for the environment, because if the radiation gets into the atmosphere, the smog then, if it was like this metal box, the smog then traps the radiation in the Earth's atmosphere and it cannot leave because the smog particles, like this container, keep them from leaving. Right? So that's the argument of why carbon emissions are bad for the environment, because they heat up, they keep the radiation inside the Earth. Okay, and again, that's a theory. I'm just explaining it to you so you understand what the theory is. Okay, you can go through Newton's law of cooling. All right, but it's saying that the rate of cooling is the change of temperature. Okay, so if you said something cooled in a matter of time, the rate of change, the temperature change in that amount of time is the rate of cooling. All right. The proportionate to the temperature difference, change of T, that's what triangle means, change, between the object and its surroundings. All right? The law applies to warming also. If an object is cooler than its surroundings, then its rate of warming is also proportional to the change in temperature. All right? Global warming and the greenhouse effect, that's basically what I was explaining here. So you can read through this, but it's the same idea. That as solar waves come in, they hit the Earth and they bounce up and they hit these particles or these carbon emissions and they get reflected back to Earth. Okay, so that is the argument. Some of them escape, right, but not all of them. So here's the greenhouse effect, is that as there's this barrier, the radiation comes in these short wavelengths that are able to get in, but as they're longer, okay, once they reflect, they're longer and they won't be able to escape and leave. Okay. Moving on from heat transfers also to now what's known as change of phase. All right, so you should be able to know, like, going from solid to liquid, that is melting. From liquid to gas, that would be evaporation. Okay, but there's also other ones like solid. So here was evaporation from liquid to gas. All right, but there's also others. You have things like condensation and sublimation. All right, sublimation is if something is solid and it goes straight to gas, so it skips the liquid form. That's sublimation. And then there's one that's called deposition. Think of deposit. Deposition is the opposite of sublimation. It goes from gas all the way to solid, again, skipping the liquid phase. Condensation is the opposite of evaporation. It's going from gas now to liquid. All right, condensation, you see it on your plants, on flower leaves in the morning. You'll see gases in the air. As they're cooled, they attach to the colder leaves or the grass, and you see condensation. Right? You can also see condensation on your car. That is the gas molecules cooling when they touch your metal car through conduction. Okay, so they are cooling. All right. Here's an example of condensation of water. All right. Moving on. Boiling is basically evaporation, except for you are adding heat to it to create gas. All right. So boiling is again going from liquid to gas, but except you're not doing it on the surface. You are doing it throughout the substance. Okay. Continuing on, you can see a pressure cooker. The tight lid of a pressure cooker holds pressurized vapor above the water surface, and this inhibits boiling. In this way, the boiling temperature of the water is increased to above 100 degrees Celsius. So therefore, the water cannot boil because the pressure is too great to allow it to boil. Okay? Now, just really quick, if this pressure was too much, right, the lid would explode. Okay? But because the lid is so strong, the pressure creates it so that the water cannot boil. But if you did put enough heat in there, if you did, put enough heat under this and it got hot enough, then eventually the temperature would get so great that the water would boil and the pressure would become too much and the pressure cooker would explode or the lid would blow off. Okay? Melting and freezing. We already kind of talked about melting and freezing, but melting going from solid to liquid, freezing going from liquid to solid. Okay? And you can see the differences between the two, liquid and ice. All right? And what's happening. Now here you're talking about an aqueous solution of NaCl, that's sodium chloride, all right, which is basically just salt. All right? If you have salt in water, it makes it so that its freezing point and boiling point are higher. Okay? Just by throwing in that sodium chloride in with the other water molecules. Okay? Energy and change of phase. All right, so this is very important. I'm going to spend a moment, and then I think this is the end. This is the last of it. But when you go from solid to liquid, all right, when 1 gram of water is changed, there is a amount of energy that is released. The same thing goes from liquid to gas. All right, a lot of energy is needed to go from liquid to gas. Not as much as needed to go from solid to liquid, but energy is released when you go from higher energy to lower energy, or higher temperature to lower temperature. And imagine this. If the gas is going to become a liquid, it's going to lose temperature, right? So where is that temperature going to be? It's going to be released, okay? And so we call the energy to go from liquid to gas because you have to add energy to the liquid. So you have to heat up the liquid, so you need energy. This is called the heat of vaporization. For water, this is 2,256 joules per gram. Okay, so that's very important to know. 2,256 joules for 1 gram. So if you had 1 gram of water and you heated it up to make it into gas, it would take 2,256 joules. Why? Because water has a very high specific heat. Okay? You also have the heat of fusion. What is that? That is, for water, 334 joules per gram. Again, the heat of fusion is the heat that is needed to go from liquid to solid. Okay? From liquid to gas, heat of vaporization, or solid to liquid, liquid to, if you go from liquid to solid, heat of fusion, solid to liquid, again, heat of fusion, you would use the same number, okay? Heat of vaporization, liquid to gas, gas to liquid, heat of vaporization. Now, what's very important is to understand, if you're going this way, the water, okay, is absorbing the energy, so you need energy. If you're going this way, you are releasing energy. Okay, if you go from gas to liquid, you are releasing 2,256 joules per gram. If you go from liquid to gas, you need 2,256 joules per gram. You need that energy in order to go that way. Okay, so we should do some practice problems. Let's see if we can look. All right, well, distinguish between heat of fusion and heat of vaporization. Heat of fusion is going from solid to liquid or liquid to solid, okay? Or the heat needed to go to melt a substance, to break down a solid, and also the heat that is released when a substance goes from liquid to solid, okay? Let's see if there's any one-step calculations. I think there's just some problems. Let me see. Maybe I'll do a second picture post where I do a problem, and I'll do one of these. I'll do one of these problems so that you can see the heat of vaporization or the heat of fusion. Okay, so like for this one, I'll do this problem. The heat of vaporization of ethyl alcohol is about 200 calories per gram. Show that if 2 kilograms of this refrigerant were allowed to vaporize in a refrigerator, it could freeze 50 grams of 0 Celsius water to ice. Okay? Also, on your worksheets, you should have had several of these problems, which I'm going to be going over this week, so you should be able to see how the heat of fusion and the heat of vaporization are done. Again, when you do your worksheets, you'll get credit for doing them. If you got the questions wrong, it's not that big of a deal. You will get those, I'll be grading 3 questions, as I always do, of the worksheet, but look over the answer sheets, the answer to the worksheet, and that I'll be posting. All right? Hope you guys are doing well. Again, if you have any questions, let me know. Don't hesitate to reach out. All right?